Alright, in this video, here's another example of partial fractions decomposition, but when we factor this, notice I'm talking about an irreducible quadratic factor. So let's factor the denominator. All we have is a GCF, so we're left with x squared plus 3. This is a linear factor, this is a quadratic factor, and we cannot simplify this down anymore. So when we break up into our partial fractions, we just can't put a constant like some capital letter A, B, C, or D. We can't just put a constant over this. We want to put a linear factor up top, or some type of linear term with two letters, so to speak. And let me show you what I mean. So let's go ahead and break this up using partial fractions. This will be equal to, since this is a linear factor, we can put a constant over that one. Since this is irreducible, this is factored as far as it'll go, we cannot put just a b over x squared plus 3. Since this is a quadratic, we want to drop down 1 degree. When we drop down 1 degree from a squared, we still have an x left over. But think about, old school algebra, y equals mx plus b. We have two numbers here. We have the bx plus some constant. We can call it d, and maybe I should call it c, just to make things alphabetical here. But again, the reason why I did this is because this factor will not factor anymore, and since it's a quadratic, we need to drop to a linear, not just a constant. Notice this degree was linear. It's an understood power of 1. If you drop a degree from 1, you do have a constant. But we don't have a degree of 1. We have a degree of 2, so we drop down to a degree of 1. But we still want to include 2 new letters, because you can technically think of it as being some slope and some y-intercept. If you think of y equals mx plus b, we do have 2 numbers that make up a linear piece. We might get 0 for one of them, but just be careful with your irreducible quadratic factors. That's the big thing to watch out for here in this example. So let's get common denominators. It's not that bad. To get these common, we need the x squared plus 3. So we'll put the x squared plus 3 at the top. And for this one, we just need the extra x. So we'll put the x up top. So let's copy this down. This is the same thing. Whoops. When we clean this up, we now have, distributing the a, we have ax squared plus 3a. Then we have plus bx squared plus cx. I'm just doing some distributive property. And we can now write this as one fraction because notice our 2 denominators are common. So we have x times x squared plus 3. Now that our denominators are common, we can kind of ignore them and we can focus on our numerators. So we have 1x minus 3. I'm just putting a 1 in front of there. You don't have to. I'll talk about it more in a second. Is equal to, let's group our, let's group our x squares together. So if we have the x squares, we have an a and a b. So I'm factoring the x squared out. Notice if we distribute back, we have ax squared plus bx squared, and that's exactly what we got right there. The only term we have with the x in it is this c, so we have plus x times some c. And then our constant here, 3 times some constant a. Now, since we're trying to get this side equal, these 2 numerators, trying to make them equal, notice this side over here does not have an x squared. So how do we get rid of this x squared? Well, the only way we can get rid of it is if a plus b was equal to 0. Because if we take 0 times x squared, the x squared would completely go away, which would help us match up this side. All right, looking at the x term. Over here, the coefficient of x is 1. Over here, the coefficient of x is c. I mean, you could write this as x or cx instead of xc, but the coefficient is c, the coefficient is 1. That means that c must be equal to 1. There's something that's going to help. And then over here, notice our constant term that does not have an x with it, 3a, must be equal to the constant term over here, which is negative 3. So therefore, if we solve that, we should get a is equal to negative 1. There's another piece that's going to help. Now we got to find b. So since we know a is negative 1 plus something has to be equal to 0. Well, negative 1 plus 1 must be equal to 0. Therefore, b is equal to 1. So using these for our partial fractions, we can go back up to the top, and using, now in my other videos, you recall I said ignore this common denominator stuff. So what we'll do is we'll just go ahead and write this partial fractions is equal to x minus 3 over x cubed plus 3x, that's just the original problem, is equal to a over x. Again, don't worry about the common denominator stuff. So we said a was equal to negative 1, so we have negative 1 over x plus, again, ignore your common denominators, so we have plus bx plus c, 1x plus 1, bx plus c. So we can just write x plus 1 over x squared plus 3. This part right here is the partial fractions for this rational expression right here. And feel free, if you want to go back and try to combine these two fractions together by adding and getting common denominators and all that stuff, you should go right back to where you started. But that's it for this video. Hope it helped.